just tell you the first two talks will be till 5, now 5 to 5:30. At 5:30 we'll have a break for tea. Then we'll have, I'm told there are samosas. And then, and you're all invited. And then at 6 we'll resume and we'll have the last lecture for an hour. And then we'll take questions to I want to and the late Professor Smocking. What I know today for you is, for those who don't know, talking about the brilliant theoretical physicist who made profound contributions to the physics of black holes, and who incidentally also suffered from European disease, which made it extremely difficult for him to talk, and was weak in the era when the new technologies were able to communicate in actual motion. So his view and so this is what I say, and I play for you in voice.
Said as such greater effect nowhere that work than in the case of black holes. Black holes are greater than anything read by science fiction writers, but a firmly matter of fact.
And it is this great story that we're going to hear about today. I'm not going to talk much longer, but I want to those ever pictures say for black hole, which is the technique of black holes are black and
shows on the cover. It is shooting out of settlement way, marking to mass. I never believed that this was ethical set until we saw that. This is the first step I made about it.
The story of black holes is much older than this discovery announcement, and we are with Professor Suneeta, please come. Professor Vardarajan is a PhD Institute of Mathematical Sciences and because of this after PhD became a then she was a faculty member in and she is very good and better from Pune in 2022. I should say actually both on the same topic, and it's a huge pleasure. And now it's here on presentation.
Thank you, Suneeta, for the introduction. So I'm going to go about black holes, despite the English just saw, I'm going to say really important part. Now, if I do that, I'll tell you what is a black hole. So first I'll tell you what black holes are. Then I'll tell you why you should care about holes for real. Okay? You saw the image, right? So that they're for real. And then I will tell you why they aren't actually black and emit all sorts of particles. So finally, I will tell you why this particular property of black hole that emits all sorts of particles actually leads to a paradox. So we say something is a paradox, so it's a contradiction to the physics that we know. So what is a black hole? Let's first understand that. I mean, this was something which was shown very early, this particular observation. So it's a region of space-time which signals can reach outside. So you see this image which you just saw a few minutes ago. There's a black region in the center, so the black hole is somewhere inside. It's not a complete region, but it's inside. Okay? So that's the black hole region. So the black region inside is a region which no signals can reach out. Now, theory predicts, I mean Einstein's general relativity, which is a direct gravitational mass theory, that theory predicts that black hole. Okay, so nearly 8 years ago, it was recognized if you take off your start, the mass is just a few times the mass of the sun, then it starts collapsing under its own gravity, and its collapse could lead to this strange object called black hole. Okay? You can start the whole material of the star just like a fluid, so you could take all fluid and put black hole. So this body where they were in a situation where object was inside them. But you should notice that that's when they arise, not collapse, even not center. That's what we say, theory predicts black hole. Now, what kind of stuff does it? It starts from the sun, or some pressure coming from matter. But if it's orbit is pressure, that's just a there are also two these cycles with a billion miles and the light is the image that was not below the black and it's possible. No, the cash is the space. It was the visualization of the could have touched on the book and you know it's exactly and that's fine. I think the aspect is getting close to that could be. Because the box is in space, can't horizon is few people we follow some reason to look at it. Some people look at it. It's not this arc. Right? It's not and its radius is roughly 9 stones. Now you might tell me that this is event on the map of space that you constant mass. Then a person is GM. Nothing special to relax, but the wrong standard doesn't take the same. No, the star is symmetric and elastic, so radius is decreasing. Actually, it's very simple. Then what is one of the atoms? It has a time. So it's pretty but then it's all like so it also something by something so it's really and you feel it's not obvious. It gets one that is like and first it's at that. So so there's some radius. If you cross the radius, normally can you not the theory is infinite. So after there's any winner element, observation is also ordinary. So it's ordinary uncommon number of mass. The system is called binary black hole. And you see where the two black holes are firing in a quasi orbit. It's as similar to the initial phase, but right way, basically it was always around it. So all concepts of pulses of space around it. And it's actually the same they merge one. And merge do is energy gravitational waves. And finally, they have one black hole which circles up its equilibrium state by emitting these gravitational waves. So what is the difference? We have two data cycles. We have 18 gravitational waves of black hole. So symptoms of the merge itself is equal to yes, I wouldn't place it on them. And we enough this one. So we see this is a solution black hole. So it's a different solution black hole. And that's something we are really happening. So I do it just like. So my result on the gravitational waves, I mean the black hole form the merging. Gravitational waves at this stage oscillate frequently stretches to back. Those sequences are not characteristic of the several layers of two building. They are characteristic of inner black hole, they black moment. But these sequences are characteristic. So this is gravitational waves. So it is I find so and frequency for these lines. One of these are processed by black hole which gravitational waves down. It's kind of images. Because our is like for the way that the this one. But the sun has its own mass and no black hole and so some things visible in units. So these puzzles happen in local banks. But because the single banks in any process always plays always should say. No black hole is So, I postulated like the multiple increases into the role and that change to MSC. And it's the area. These three are the relation of between it, with the unit. It's unit. The chicken must be the horizon area at chingal and position. Where is on on them and may not be possible. So by constant, take this differentiation analysis of black hole. Take the cap constant by zero of the okay, so these names. That's how black hole behaves in the dynamic. So we will a little bit. But look at those black holes. Ruler. Compare it to all instances of the flow states change in input entry and change one. So that's now. So theory in the activity equation. And sort of analysis of equations. For the component and the line of energy content. And simply the channels and energy equal. There is some relation between the then you have to be the flow dynamics. And you just say argument that the entry will be proportional to the horizon area which you have. So if you stretch the other cap over temperature and this is something like PTV because it's not gas temperature but it has space. Now this suggests as a multiple kappa is like temperature and recall we said kappa is constant time temperature is also constant in the dependent by constant for Z law of black mass. Further argument from that always something influences and that is the black hole entropy outside. Is this relation equation is an analogy? And now I want to relate you to this analogy. Okay, so let's understand what is it? What is it? It's a system temperature of the surface of the period also. For the average of the surface is about 6 degrees centigrade. Okay. Now here I have not told you what is the constant between kappa and temperature in this equation. But one thing which we do realize we prove this kappa is equal to 1 over another. Okay. And in fact, how from this bridge, I mean, the which is approach kappa, what is the mean? Okay. What do you generally use to explain the math? The math is actually everything is fine. Okay. So you use one which is math, that is really black. It actually behaves like a black body. Okay. So you know it does radiate like a black body at a temperature which is kappa 2 pi. Okay. And you can put numbers and you can see if you have a black hole which is comparable to this warm temperature and temperature minus 8 degrees centigrade. Okay. So not physical radius or if it came a black hole. Rather, the black hole radiates like a black body at temperature. So if you're a college student, you know that black body radiation has several frequencies and which energies, the spectral frequencies, they only on its temperature. So that's now, let's have this temperature proportional to 1 over the mass. As the black hole radiates, let's say for the radiation. So as the black hole radiates, its mass decreases. But this temperature is proportional to the mass. So the temperature increases. We have a black body at high temperature, it will radiate more, and it will radiates away, leaving behind more radiation at that temperature. Now, if you study some thermals, and if you know about pure and mixed states, then what you would characterize thermal radiation as being in is a state. This is from matter. Okay, maybe it's a all matter is eventually quantum. If I get a quantum formation of a black hole, the black hole was from a state of matter. I know every information about that state, okay, one state. But if I just radiate away to disappear, leaving my thermal radiation is a mixed state. Now, all evolutions are quantum. Quantum evolution can bring a close state to a mixed state. So what has happened that we have all information about close the black hole is formed. Since final radiation, they characterize the only on M. This is a path because we cannot lose information in quantum evolution. This is information lost. As long as the black hole is by no means a dogmatic material. So the information is subtle and so it's actually all the black hole couldn't be placed by a resonance on. So there are all ideas because it's such a thing. Now let me just give here's a picture of Hawking radiation. I want to do that size figure, but it's a very powerful eye that has that has reused to the community. Now what happens is suppose I have a black hole and I initially start out with matter which is in a zero energy state. Okay? We call that the quantum. So matter is really in a zero energy state. Yeah, so but this small vacuum, what we know from quantum physics, we understand that this quantum vacuum fluctuates. There are lots of fluctuations can be thought of as companion pairs of particles that are reduced and then annihilate to that. Okay? So these are virtual entangled particle pairs and only last very short. But what happens is, if you have a black hole, you also have these particles that have been created and destroyed, and if you have one house negative, but you have the one that can fall into mass. It doesn't technically fall, it comes through, but it's understand it. As negative energy falling inside. Now, negative energy particle cannot okay, the black. Not just inside black hole. The point is, when we call it negative energy, loses it's not any image. So it can exist in horizon, and the output will less. Okay, so energy particle is seen as radiation. So you can think of this radiation, which is called Hawking radiation, as these particles, which are particle pairs. Particles, one of it falls inside, it has negative energy, so it goes the mass back, and the other one is seen as radiation. Now, see another part anyway, we are seeing the context. When we have corresponding energy, so this picture of particle pair, one of it goes in and the other goes out. Okay, and this suggests the picture being animation to look out for Professor like a Taylor's talk, which is going to be in that. And I want to end with one slide. We have seen that black holes should have an entropy in order to second of thermodynamics. In order to thermodynamics, system has entropy. It has many entropy. One system has macroscopic description, average description, and a statistical description of this. Around the many microscopic from that one macroscopic state, like energy order. Okay. So this entropy, this thermodynamic has situation, the law, not microscopic of this. We all like the microscopic state. Such a prediction. Or microscopic. But the all microscopic is exactly the entropy, which really is right divided by 2 times g because constant. This is the states. Professor Nabamita analysis on the two different work of and add system like a few.
Before we have we studied how it's in I was to a grant. I want like if I can point somewhere, I can't. Excuse me. Because Professor Banerjee, she did her research at Harshan Research Institute in Allahabad, and this is on black hole physics and string density. That people have done their research on some and they're really experts internationally renowned on the subject. I'm proud to say that both Suneeta and Nabamita have attended. I got both of them at some stage in their lives. It's sort of inspired for me. Now, this contained the classic result. A class relation between black holes and fluid dynamics. I couldn't substitute one to it. That's one to it and water flow of quiz. There's a very very old. It still it's the modern version of it, and she has worked on thesis and highly psychology. There is that after PhD she went to the University of Netherlands and to be in the Netherlands in Amsterdam. There will be Indian students for the collection in Kolkata. There was a student who was in which famous experiment was in Institute of College. Come on. Yeah, Raman effect and also in fact relation to legendary results in physics came out of this. She moved so very happy, and then she moved Bhopal, so again we went for that, and she asked it. She got given the prestigious grant Netherlands was there, and you now do your that's not up my way.
Thanks. Thank you, Sun, for the introduction and for all this pleasure to come back by Sir. Thanks for slides. So, Suneeta for introducing us today, and I'll just do a little bit forward a bit, and I'll do about what is our black hole made of. Okay, and as I go ahead, you will see that the answer is not this one. Okay, there will be a later answer to these questions. And hopefully, by 30 minutes, you will have some idea. So let's start. So what do you mean when we ask this question that what is something made of? Okay. For an ordinary object, what kind of material is this? Wood, I mean, this is tea or coffee, you can think of. So it's like definitely a polymer and some other things into it, or to be more scientific, like what kind of atoms they are made. But for black hole, as you will see, answer is a little different. Okay? We'll see by the end of the talk that that's what Suneeta said. Black hole actually made of, when you talk about geology, information and processes. These are the words that are already used to you, and let us see how they do. So let us then first take you through the family of objects, like planet, stars, what else. So okay, the first one has to are actually stable, yes, gravitational. So they do exist and they are not body. But stars are not like that. As talking about this, that's not interpreted as, and that has where gravity was happening. And waves pressure they collapse stars. So stars can collapse. That's stars are formed because of star around. Then what about that? So let me give you the simplest answer. As soon as you the form, a big star collapses under its height. So notice that we can think of it like that. That this collapse happened that can support this force of self-gravitating force. So it went that. So and the collapsing matter actually precise time. Precise time. So what happens? We really call actually spin of this collapsing matter, and that really called anything about geometry. And the most incredible statement is that all the form which is nothing like it's very different from the class, different from all. It's different. It's so complex. So I was saying, that was right. So I told you right that they may add some butterflies and something to put it under. The thing is my inner was the same. Let us ask that this is different because light and sound. So even light can differ. Why? Why does that happen? So after that, almost like in your students has to about concept of velocity. If I throw something standing on these eyes, the stone will come up. So it cannot escape. But we know that we can believe that there is a different velocity. It will go effect of the rotation and pull apart. It will escape. So now a similar question we can frame that. Can we think of object from where light comes? That's what we said black holes are. So already it is definitely not science, but really can we have this collapse that we are talking about? Can we really thought that our collapse has been an object has a now light to come? This calculation will do it is possible. If the entire mass is the rays of this value of course, I'm assuming it to be spherical matter here. If the mass can be considered to be radius r is then the light amount. So the same thing as Suneeta was showing you in the viscosity of light being equal to 1. So okay, that's it. I really think about such a amount. For any of the normal rays, for example, RS, if you really think it comes out to be 1 centimeter, where I know that the radius is almost 200 meters. So we cannot have light. The question then is, can we think about any object? So where the left hand side is a normal body, this blue is rays are directly. You can think of opposite scenario. Here the rate of is and point is okay. And the answer is yes, that's exactly what is happening. Okay. So when we think about question and think what object is here. So now to understand this, like back again. Know that if we have massive object or gravity at stake, and the simplest law we have learned from class 2, maybe in 20 but if say like this is the center and anything else taken in the car, I will act there will be interaction point between the having that sun is very massive and thinking about how the arc is going to move with a very particular give rise. Now this is very simple if we really understand that because we can tell this in terms. So under the problem of Einstein's theory of relativity and we can give you another thing. Let's now understand how bigger how motion our sun will look like in Einstein. So Einstein's theory it says that any mass here for example what we realize it space time is both complete. So here the what is that around space and time is like it's not it's part and this is space time but it's not space. This is like choice. Basically this is just part in that class. We straight lines, right? In particular you can see that light if it's talking about light. So the massive body we have changed our view by understanding the same aspects. So the question about that the first black hole solution, the first kind of black hole, how I call it shine in C. And then you have that system. So what I have written here, if you do not understand it, it's fine. Just say it would be a source, the difference between 2 points around the system, class space. Okay? So then you go back. So I'm just telling you that if I think that this object, so this is black, it's like around it, there is a short system. What is the for this is the system, the alien system. Every one is upside down. It's going to be on the it's the same object that I talked to you about. The single gamma is to be expressed on the machine. So whenever this R is better than R is but on the next but when R becomes below is the value is close to R equal to R is something to be happens. For when R is less than R, you can see very clearly that mountain. Now at from us, there is and here yes. There is an explanation based on the intelligence. But the same Charles found, you must carefully, but please check here. So we are actually given a short shapes, but even not getting. You see that something more interesting about it. So let us first understand this R equal to us. This is again talking about the testing that is flowing out. And the velocity of the water at various speeds are different. How it is the first speed less than the light, whereas both go for the same rate lap of increasing. Which is and maximum velocity at the which is you see when fish will be on the right side of the rate, still but the fish is on the right side of the track, it's not your side is that. So we just cannot be and it will be flat. That is there's a cartoonish between that clinical is going like that. And what is more precise then this is actually you can say value as both in and out which are directed like rays actually both are decreases and here inside of it like nothing came out of it and light came out of it. Good, please understand. So now let me understand the question for the black hole. Well, the first meaning that it doesn't allow light. So you are outside the outside question answers for black holes. The question is, well, second it was back. So now how is what is happening? And second is almost finished back. What is on the syndrome? They go to question that you already hit. So I'm trying to get an answer. So let's get common physics first. What I mean, what heat, right? Ordinarily heat comes when mainly invisible, from invisible to motion. Listen, so you can ask this question, what are the and second the whole with me? Listen, so if someone familiar with microscopic sets, just believe what I mean by it. Just and say the only information that you have is heat. Say it's in. Then you see from that all these balls, this balls has four, it has four, and four of them has all the information you have. But see, those four balls at an actual in different. So suppose that there are actually this thing four sides done. So if you click on the information of the last, there are these different ways of it, but there are. Okay? That's what we mean by process. Maybe a black hole, you're talking about it. You can have different estimates of the small charge inside. So okay, maybe different. And we can't answer those estimates. We like it. So thermodynamic behavior strongly suggests that the underlying quantum sequence of black holes and current just from that. There are really many mechanisms of chemistry for and this microwave night. This quantum sequence can actually work with this. And this because this energy that will state the level of that is the usual thermodynamic relation is responsible for the then this question can be called root to extent entropy. That relates what these processes to black hole. So it has a regular entropy. I've already done entropy, but the thermodynamic we should come forward and we do find. Okay. So this we find family picture of quantum structure. Who have this known as secondary for the knowledge building of some sea level. To understand concrete, we definitely need to be available and other characteristics such as actually becomes that entropy. If you are black, it's not the way. We take a small piece and we find. Let's just think about the black hole geometry. As the effect of quantum field, this is the music that we talk about. We have a black hole and there are other quantum fields around. In particular, they also have cube and appear and get this Hawking radiation. Can be a concrete allocation effect. Then so I'm giving you in a mobility logic. So it's a black hole. I'm just thinking of black hole is a geometry and I can have this radiation. This can have to come negative. That's such space. This fucking can get to state like this. But no problem. It fails to some gravitational efficiency. It is paradoxical. Although first now. If we understand it, then we really need a full quantity. This is what is known as the culture. I feel what bacteria gets tested. That's the most to people is now which describe the condition of the bacteria as more of that. So we need to do that. So speaking as a function to it's very rare objects and not particles. I think there's an act not that so you can any X-ray object dimensional field. This have properties and these are the basic constituents of stability and it's gravity the quanta of the resistance. Now to determine that how and these different quantities associated with that whole So in this, of course, not for apples, but some apples, you have ice restriction. You can ask that direct string is stable, and this is equal, not really, and form of it. So you don't have properties of black hole, certain properties of that actually go back depend on other picture where I have size, and maybe I'll be able to think that how different light objects to get all those quantum states, which I will have as well. Which class of maths is a field where I have a relationship, PhD works also. We found that generally of these objects that will take infinitely and much more than that. Okay? So it's not only that Hawking object can understand, but can understand even the questions from it more. How they even understand a different direction of inside we will get of one has a better understanding of associated atoms that will etc. So this has been done. In fact, okay, as I said that this extreme black hole, the black holes which are very different. And now to a very special tool for field much more. And that is a processing function, the function and point that the part of the black hole parts specialized very well function is only over here for isolate, but black holes is after all is found inside at what which time it has another structure for circles. Somewhat universal and this is what we can understand this computation. This is more than just community and has about this is what it directly go to a similar near level. If you remember I told you this other thing of black hole, this is the boundary again. For example, I will do the layer this is like 0 point at near black holes where the prices are not considered. If I shown here prices, if they were just for another, I'll let you know the temperature. But if they are very close, then I assume. Now for the as good as black holes, they eat together. And we'll get very nice results from it. So also see what just what needs. So I that it's something of the term of interest. The entropy that can be that review, we know what a quick is possible. However, the kind of universal structure out there for extreme and extreme. Okay. So but beyond the class and beyond the technology, there is a two object that's very sophisticated and it's not a smooth. In fact, of course, because here is the I know I talked about also the horizon microscope, the condensate that maybe not just like first. But this what you don't have fine. So I try to say it is really and in space inside. That is not in the classical geometry like this perspective, but results some smooth and therefore in horizon what is so it is also not standard and there is much. So that give you the full answer. So that's definitely not only definitely not fictional and it's very much real it's entropy and reference perspective and in terms is the microscopic quantum sets whose complete nature is being uncovered. So that's
Thanks, Nabamita. I'm Dr. Prince. Please welcome back and Rebecca, and we'll do that at the end of the last question. Speak now for team episodes. So, please. second in waiting. Real pleasure. This is important. It was interesting. I was in Utrecht as a postdoc, and so was Nabamita, but a few years apart. Did you ever meet? You did? Okay. And then she was at Amsterdam University as a faculty member, and then moved to Southampton University in the UK, and somewhat recently moved to Birmingham as the Pro Vice Chancellor. She is and she's the Pro Vice Chancellor of Engineering and University of Birmingham, and she works with the UK government on technologies and AI-related themes, as well as doing research on black holes and black hole physics and string theory. She is moving to the University College London, which is even bigger and even more famous than the University of Birmingham. And she won the in Europe, I guess, she won the prestigious Arthur Prize of the European Physical Society and a number of other honors and academic fellowships and so on, which I don't have time to, and I don't want to stand between you and this talk. So with that, I will leave you to the lecture.
Okay, thank you very much. So thank you very much for welcoming me here into Pune. I think it's my first time visiting IISER, and I'm overwhelmed by how beautiful the campus is. And I have to say the rain is wonderful because we've been having anomalously hot weather in the UK, so it's nice to kind of cool down. So in my talk, I'm going to be sort of, repeating some of the things you've heard in the two previous talks. I think I'll say it probably a little bit differently, and I've got some pictures to sort of convey. But I want to draw out from this some of the sort of, the puzzles and the questions that we have about black holes, the sense of why people have been working on these for so long from a theoretical perspective, why we see them here. So this talk is really about black holes and quantum computers. So I'm going to discuss some surprising relationships between black holes and quantum technologies. So just the suggestion that black holes would have anything to do with the physics of fluids, water and so on, was a bit surprising. But at the same time, for many, many years, we've had some sense that black holes, have a behavior that's like fluids. The connection between black holes and the idea of building a computer using quantum properties of atoms, quantum technologies, is perhaps more surprising. But that theme has sort of been dominating some of the high energy research over the last decade or so. So black holes, a kind of concept which has appeared in science fiction really since the 1950s. And one of the wonderful things about when you come to talk about black holes is whether you're talking to people who are still, in elementary school or in high school, or talking to people who are older, they actually have the terminology and the concepts. They have it from, watching things, watching movies and so on. So all of the things that you see discussed actually have their roots within science. So of these three pictures, I think the top right-hand side is one that will be familiar to many of you in the room. So this is the black hole who plays, which plays a very important role in the plot of the Interstellar movie. I'm not going to talk about the role of the plot for those who haven't seen it. But what I am going to talk about is a little bit about that picture, and what that picture means. So that is a picture which has been created, of course, by the Hollywood teams, but it captures real physics. You know, it captures sort of behavior which is predicted by Einstein's theory of gravity. Now, some of you may be fans of science fiction. That's the TARDIS on the right-hand side. Fiction program of enemies, you know, Simon and things of time distortion. The left-hand picture comes from a not particularly well-known movie from about 30 years ago, but the reason I've picked it out is because of the title. So we've used several times already, you know, in the description, the title of Event Horizon. Many of you in the room have a sense of what is the event horizon of a black hole, even if you haven't been, you know, studying physics at a high level. So now let's come to quantum computers. So, you know, the basic concept I want to get across about quantum computers is that they are harnessing the behavior of matter at the quantum, at the atomic level. And so, you know, at a very basic level, how does a classical computer work? How do the computers that we all work with operate? So essentially what it's doing is storing information, and storing information in binary form as ones and zeros, and then you're processing that information in of ones and zeros, and, you know, turning it back into sort of, you know, complicated modern programs. But its very essence, that's what you're doing. Now, a quantum computer, the idea is that it's storing things in, you know, and the picture here, I'll give a slightly better picture in a moment. The idea of a quantum computer is that in the quantum world, there's an uncertainty. You know, there's always a probability that you're a 1 or a 0, but you're not going to collapse to be sort of precisely a 1 or a 0 until you make an observation. And so there's an inherent uncertainty. So the fuzziness that is shown here is that sense of this sort of fuzziness of a quantum uncertainty. And the other thing that this picture is a quantum computer, rather than sort of individual bits of information, they tend to operate much more coherently and process entire sort of states of information. So the picture shown here, you're taking all of this complicated thing and you're doing an operation. Now, this is a very simple picture, but I like the picture for sort of several things that it conveys. So one is this sense of sort of uncertainty, whether you're in a 1 or a 0. And the other is the sense that actually, what would quantum advantage be? Why are we interested in quantum computers? Well, one of the reasons is that if we can simultaneously process large amounts of information and they are, you know, correlated with each other, we have the possibility that we could actually process faster. Why is this important? Well, it's important because, you know, computer chips have improved a lot over the years. So for those who've had, you know, computers back to, you know, when personal computers have seen an incredible speed up, we know that this is going to come to limits. We can't actually get classical computers to go any faster because we're actually coming to the sort of the limits which are set by sort of, you know, atomic separation. We have to really start harnessing the power of, you know, the properties within the atoms to actually get sort of computers that are going to go faster. So as I was saying to somebody, you know, today, if we're looking at the technologies which will define society at the, you know, the second half of the 21st century, we really have to think about harnessing the quantum properties, whether that's for computers or whether that's for other things that we would do, whether it is for sensing, whether it is for, you know, very precise timing, whether it is for sensing in the context of medical instruments. So in, you know, some of the, you know, the breakthroughs in technology in the 20th century for medical technology really come from sort of, you know, building sort of sensing devices which are able to, you know, scan us through CT scans and MRI scans and so on. But actually to go further than that and to, you know, to deepen our areas of sensing, we need quantum technologies. All of this preamble is to sort of, you know, give you a sense of why people are interested in these subjects. Now, another sort of, you know, intuitive picture of what is going on in a quantum computer. So I said in a quantum computer, you don't store information as exactly 0 or exactly 1. It's in a sort of, you know, a probabilistic state that it could be a 0 or 1. And I've also said that you can think of this in some sense, is being captured. You know, you describe your quantum bit. It can be realized, you know, through factors. You know, this isn't to talk specifically about quantum bits and quantum information. So I'm not going to go into the details of it. But the picture is to sort of give you some sense of what you're doing. So the picture on the left is meant to convey to you the sense that you've somehow got this atom, this electron, and you're holding, you know, this in, you know, a particular kind of quantum state. So the sort of vector there is kind of, you know, the vector is telling you about the probability that you're a 0 or 1. And as you rotate that vector around, the probability that you're a 0 and a 1 changes. So that's how you're storing your information. And then when you're, in a sense, doing an operation in a quantum computer, so in a classical computer, you take your 0 and you either it stays as a 0 or it stays at a 1. In a quantum computer, essentially what you'll be doing is rotating around these probabilities. Now, so for a single piece of quantum information, this is sort of shown here as you comes and actually change sort of, you know, the probability that things are 0 or 1. Actually, the interesting thing in a quantum computer is that you might do this simultaneously, not just on all of your bits of information, but on multiple bits simultaneously. So, again, not to talk about all the sort of the pieces of quantum computing, but let's talk about some of the, you know, sort of challenges of this. So, why is it that we don't, you know, walk with quantum computers? So, there are challenges. So, even if we come up with a, you know, an idea of how we want to realize a quantum computer, we actually have a lot of engineering to do. So we have to design and build hardware. A lot of the kind of prototype systems which are sort of built in physics labs actually have quite a small number of quantum bits. So they might have tens of quantum bits. But if you think about the, you know, the numbers you're used to when you talk about your phone or your computer, we talk in gigabytes, terabytes, right? So these are very large numbers. So scaling that up is one of the biggest challenges of quantum computers. You know, that is something, you know, because it's quite complex to actually sort of get these systems and actually get more and more quantum bits in them. And one of the reasons it's so complicated is, you know, everything which is a positive always, you know, comes often with a subtlety or an issue you have to address. So it's absolutely great in a quantum computer that you're storing things in a way where things are correlated with each other, things are linked with each other. But it does mean that you're vulnerable to impacts from the environment. So in particular, if you corrupt one bit of information, you're vulnerable that that's going to affect your whole kind of, you know, storage of information. And that's a much bigger vulnerability in the way that quantum computing works than classical computing. And that links to the point which is written below about, you know, so if something, you know, if you're transmitting information, how would you actually correct errors? And then the final question is, in the world of computing, you know, so we talk about hardware, we talk about software. We talk about, you know, what kind of programs do you write which are actually going to use the computer. So, you know, on standard computers, we're all familiar with, you know, the standard Microsoft sort of fleet of programs and, you know, web browsers and all the things we use. But I think the fundamental question that people would have with quantum computers is, what are the things that we'd want to do with quantum computers? What are the things which we can't do so well with classical computers that we could do with quantum computers? So how would we actually design software, algorithms, which really exploit and make use of quantum computers? Where would we get quantum advantage? Now, I'm not going to claim in this talk that black holes have something to say about all of these topics, but what I am going to say is that we have some insights into those bottom two things: quantum errors, how we might correct them, and also quantum algorithms, quantum sort of processes, how we might design them. And I'll come back to at the end to why we get a very different way about looking at quantum computers from black holes than we do from prototype systems. But to preview this, I want to sort of, you know, reinforce again that the prototype systems we work with in labs have a very small number of degrees of freedom. So they're actually they're a very small number of quantum bits. And black holes give us a very different way of looking at things where there's a very large amount of quantum information. So as I said, I'm going to talk about the sense in which black holes give us insights into and behave like quantum computers. So now I'm going to go back to, in a sense, to the beginning to talk about what black holes are. And I'm going to be sort of reiterating some of the points we've already heard this afternoon, but to sort of draw out the pieces that we will need. So showing a diagram very similar to what you've seen earlier, what is a black hole? How do we define it? Well, ultimately, we define it by saying that nothing can escape from inside a black hole. Nothing can travel faster than the speed of light, and so a black hole is an object which is so dense, so compact, the escape velocity exceeds the speed of light. So the picture on the right-hand side, a version of what was shown earlier, you have a surface of a planet or a star, you throw something off, at escape velocity it escapes. But if you think about just squashing that, making it more and more dense, actually the escape velocity increases. And as you make it squash it more and more, again the escape velocity increases, and so it gets less high. And you can see from this picture, if you just keep squeezing and keep squeezing, there comes a point that actually it's so dense, it's so compact, that even if you throw something up at the speed of light, it will not be able to escape. And the speed of light is a fundamental limit. It can't go faster than that. So the history of black holes, again, we could spend an entire afternoon discussing it, but these ideas of having something which was so dense that light couldn't escape, they go back in time a long way. So, at least in the sort of 18th century and the 19th century, there were people like John Mitchell and Laplace who postulated this, that there were stars for which gravity would be so strong that light wouldn't escape. But of course, at that time, people didn't really understand the nature of light very well. That understanding came through, the middle and end of the 19th century, particularly with sort of culminating in the equations of Maxwell. And the mathematical understanding of black holes required both that understanding of light, which came from Maxwell's theory, but it also fundamentally required Einstein's theory of gravity. And again, referred to earlier this afternoon. So what is Einstein's theory of gravity fundamentally? It describes gravity in terms of the curvature of space. So here we show the Earth. This is a well-known picture, I think, from Wikipedia. Show the Earth and the fact that Earth curves the space around it. So a very different way of thinking about gravity. Now, black holes appear as solutions of Einstein's equations. Mentioned earlier, there were solutions of the equations found very early. But actually, I think, particularly in India, it's important to sort of talk about the mechanisms for which convince people that these weren't just artifacts of solving the equations mathematical, but they could really happen. And so in particular, the fact that black holes could really seem to form in nature through dying stars. So the basic point is that if you have an ordinary star like the sun, the pressure of the nuclear plasma within the sun is balancing the gravitational force. So gravity is always an attractive force. Gravity always wants to pull things inwards, but actually the pressure of the nuclear plasma burning balances that out. And the basic idea is that as the star dies, as it's burnt up all its fuel, you no longer have that kind of pressure to sustain the sort of, the star, and it just collapses inwards under its own gravity. So really by the 1930s, it was realized that you could have, genuinely a mechanism to form black holes. And in fact, from the great physicist Chandrasekhar, the black holes are the most perfect macroscopic objects there are in the universe. So Chandrasekhar realized, the possibility of forming black holes through gravitational collapse, and also, talked about, the quantitative thresholds. When would you get a black hole forming? And of course, contributed many other important things to the subject of black holes. But this slide is to reiterate something which has been said earlier. Black holes are really unusual amongst the kind of objects we see in astrophysics. So white dwarfs, neutron stars, you may have heard of all kinds of exotic sort of stars, but black holes have a really special feature. They seem to, it seems that you can form them in many different ways. You can form them by collapse, as I've just described, but there are other ways you can form them too, by colliding things or by acting as seeds at the center of galaxies. And yet, we seem to be able to describe the property of black holes just in terms of very simple solutions of Einstein's equations. So you actually describe, black holes that we see astrophysically, they're really described in terms of mass and spin. They can have charge too, as Nabamita sort of talked about earlier, but actually usually astrophysically the charge is not going to be important, and things are usually neutral, roughly neutral astrophysically, because they kind of pull charge around them until they're neutral. So astrophysical black holes we're describing with mass and spin. So to complete Chandrasekhar's quote, black holes are, so special because the only elements in the construction are concepts of space and time. So if you tell me how heavy it is and how fast it's spinning, we can seem to describe what's going on in a black hole. And we'll keep coming back to that because this is one of the big puzzles or questions about black holes. So black holes, I mean, I'm almost telling you a history story here, right? So we sort of started, they come out as solutions of Einstein's equations. We start to understand that they can form through gravitational collapse. But then for a period of years, the physics world concentrates on many other things. So in particular, many people were involved in activities during the Second World War. And then it's after the Second World War that they start sort of thinking again. They start looking up in the sky more, doing a lot more astronomy. And the term black hole itself is said to have been coined by the very distinguished American physicist John Wheeler in the 1960s. So how would you actually, how would you astrophysically discover black holes? So this is back in time over 50 years ago. What people realized is black holes are intrinsically heavy objects. They are dense objects. And you're going to sort of see evidence of the black hole from the impact that it has on the surrounding objects. So the picture on the right-hand side is a picture of a discovery of a black hole, or what was thought to be a black hole, that really came from sort of realizing that there seemed to be something heavy at that point in space, which was actually impacting on the objects which are around it. So back in the 1970s, by this time, Stephen Hawking had already been working on black holes for, I guess, a number of years, 5, 10 years. He made a bet with the Caltech physicist Kip Thorne that this wasn't a black hole. Now, Stephen's logic of this was that actually if it turned out, after all, that there weren't black holes in nature, he would have spent a lot of time wasted in sort of studying them theoretically. So he figured that he'd rather win a bet at that point. And they had various things that they bet each other. He actually conceded that bet in 1990, based on the fact that there was so much evidence that this object actually seemed to have the properties that one would expect of a black hole within Einstein's theory of gravity. So that's back in the 1970s, 1980s. Another example of detection of black holes, which was really tracked over a long period of time, is these very heavy black holes, which were referred to before. So black holes which are at the center of galaxies. So Sagittarius A star is such a black hole. It's roughly 4 million times as heavy as the mass of our sun. And again, you can see that something is there because you can see the impact, the gravitational field that it produces. You can see that things are orbiting around it. So the picture on the left shows you data from the 1990s. You could see that things seem to be orbiting around, suggesting that there was something heavy in the center. So now let's come to this picture. So a little bit of a contradiction, right? Because we said that black holes are so heavy that nothing escapes from them. And there should be something where whatever light they have is somehow trapped within them. So where does this picture come from? So as I said, this is a picture which is certainly created by Hollywood, but actually it's created also by the very distinguished and now Nobel Prize winning physicist Kip Thorne. It's based on real science. So why do we have light around the black hole? So we've already touched on this again in previous talk. Black holes are not really completely black in the sense of black on our telescopes because they are so heavy. And that means that they draw in things from the surrounding sort of neighborhoods and draw them around them. So many black holes are actually surrounded by disks where they basically have matter which is spiraling into the black hole. And when you sort of spiral matter around in sort of orbits, and you're spiraling at high speed, you will typically get Cherenkov type radiation. You will induce radiation, and that's what you see in the sort of artist visualization on the right-hand side. So here you've got something which has got a kind of a horizontal accretion disk. It's rotating so fast, things are spinning around so fast that you're actually emitting radiation. And then you also have streams of matter which are expelled along the rotation axis as well. And so actually, if you looked at the black hole, the black dot in the very, very center there of that picture is where the actual black hole is located, but the stuff which is around it is being drawn into it. Into the black hole. So that's an artist's visualization And it's meant to illustrate the accretion disk and the jet. But it doesn't really get all of the physics into it, because the black hole is such a heavy, dense object, it's actually distorting the space around it. So actually, light rays which are behind the black hole, they wouldn't just travel to us sort of horizontally as we see here, but they actually get pulled around the black hole as well. So if you go back to this picture over here, what we're seeing is in the horizontal piece, that's where our accretion disk is, but actually the vertical ring that you see is actually light from behind the black hole, which is being pulled as it's trying to escape. It's being pulled back, and we're seeing it as a vertical ring, and similarly on the piece below. So actually sort of mapping out what you see from a black hole is quite complex. So Sagittarius A star, the supermassive black hole that I mentioned earlier, it has relatively low accretion, and it emits in the radio waves. So whilst I've said the word light, actually I really mean all of the electromagnetic spectrum, and Sagittarius is actually something which is active in the radio wave source. So the goal of the Event Horizon Telescope is really to image black holes of that type, trying to get down as close as we can to horizon resolution. So this is a picture from maybe 15, 20 years ago of what people had at that point. So they had something on radio telescopes. So what they did is they brought together a whole cluster of radio telescopes, put the data together. It's almost like trying to get more and more pixels. So if you compare your digital cameras from 25 years ago to what you have on your phone nowadays, the improvement is really the amount of pixels that you have. So they used a whole collection of radio antenna, and they were able to image in much more detail. And again, we've seen this picture earlier, so this is not Sagittarius, this is M87, which Sunil showed earlier, and this is shown in exquisite detail. So the black dot in the center is where the event horizon is, and then the imaging that we're seeing in the red and the gold is actually the image of the accretion disk. And the astrophysics who study the structure of the accretion disk can then interpret how the things are positioned around the black hole, how fast is it spinning, how is it evolving, and so on. But what I wanted to take also from this picture, it's a little bit of a misnomer to say that this is an event horizon telescope, because it's not really imaging for us the event horizon. The event horizon is sort of somewhere within that black central piece, but what we're imaging with exquisite and beautiful detail is the accretion disks and the jets which sort of sit outside the black hole. Now that's going to come back to us, because if we're interested in what happens as we actually approach the event horizon, we aren't quite at the resolution that we're going to see it. So, jumping forward further in time, so about 10 years ago, discovery which hit the sort of front pages of newspapers, the discovery of gravitational waves. So a prediction of Einstein's equations, just as Maxwell's equations, which describe electricity and magnetism, inferred, they predict that there would be electromagnetic waves, so the gravity equations infer that there would be gravitational waves. So we've already heard about these earlier this afternoon, and I'm not going to spend too much time on it. So black hole collisions, that's what they saw in their first observation in 2015. And the next generation of gravitational wave experiments looking for other types of black holes. So the detectors which are based on the ground are looking for black holes which are typically of the order of the mass of our sun. So they're tens of times the mass of our sun, and they also see things like rotating neutron stars. But if you want to see gravitational waves which are associated with these really, really heavy black holes, you actually can't do it with ground-based detectors. And so for the 2030s, there is an experiment planned to actually send gravitational wave detectors up into space. So that picture on the bottom right is an artist's visualization, of course, but that's what they're going to try to do. They're going to try and have laser beams in space, hundreds of thousands of kilometers of coherent laser beams, and use those to detect the gravitational waves associated with big black holes. The thing I want to take from this picture is that there's so much exciting astrophysics being done with gravitational waves. And also, of course, India is very, is joining this collaboration, is part of the LIGO collaboration, and a new detector is being built here. Really important for sort of improving the sort of, the sensitivity, the precision, the ability to localize where your black holes are in the sky, and all kinds of other things. And so, this kind of plot shows you the sort of, data that they take. And this actually sort of visualizes what we saw earlier. So when you collide the black holes, as the collision sort of crescendos, you have a peak of the amplitude, and then it dies away again. Okay. Now, again, you could say, what does this actually test? So this tests that, the black hole, the space and time around the black hole is sort of, agreeing with what Einstein's predictions are. If you were able to detect with exquisite precision, you might be able to sort of test whether Einstein's theory is exactly right, or whether, small adjustments from Einstein's theory, are allowed by the data. And that's one of the things that the LIGO experiments are trying to do, and that the gravitational wave experiments up in space will do too. And again, I'll come back to that at the very, very end, when we talk about ideas about what's going on in black holes. So, now I want to sort of, having reviewed that and sort of put together things we heard in the earlier talks, I really want to move to my main sort of question, which is the question of what happens if you actually fall into the black hole. So again, we're visualizing here, all the colors are showing you that accretion disk. What if you really fall into that black dot? So, according to Einstein's theory, what would happen is if you're in a spaceship and your friends are in spaceships which are sort of putting out lights, as you go into the black hole, you start seeing some very weird distortions, Doppler shifts, time slowing and so on. And then as you go deeper and deeper, you start feeling some very strong tidal forces, which ultimately sort of stretch you, squeeze you so much that you're torn to pieces. And so that kind of picture really comes from taking, the solutions of Einstein's equation and asking what that means as you sort of fall in. Now, for, I think, over close to 60 years, we have known that there is something really interesting happening inside black holes. So we know that deep inside the event horizon, there's a region where the curvature of space becomes so large that Einstein's theory itself is invalid. So why is that so important? So whenever we see the breakdown of a physical theory, it's a signal that we need to sort of improve our physical theory, our description of nature. So when we get sort of, we try and do calculations and we get infinities, it's a sign that there's something that we've missed. And so when this kind of came out of, this sense that, that there is large curvatures, singularities as they're called, inside black holes, that there's an inevitability of these, which was what was proved by Hawking and Penrose 60-odd years ago, this was really a sense of, there's something here that where we have to push the forefronts of our physical description. Picture on the right-hand side is a picture that, gives you a sense of how people sometimes visualize black holes. And actually it links to why I showed you earlier this picture of throwing things off the surface of a star or a planet, and actually as things become more and more compact, more and more dense, it becoming harder and harder to escape. So sort of think about the right-hand picture as a sort of, the final point. So as you sort of squish and squish things, so as you squash things, it becomes harder and harder to, for things to escape from your surface. Now, if you're in this picture, you've squashed things so much you've created a black hole. And the picture that, that Einstein's theory would tell us is that if you are behind that red surface, if you're below that, you're inside the black hole. And actually, however hard you sort of try and push things, even if you throw things at the speed of light, they really aren't going fast enough to escape. So it kind of gives you quite a good visualization of how hard it is to get outside a black hole. It also gives you a sense of how things are kind of, coming to a crunch inside a black hole, and, you're actually being pulled and squeezed and squashed. So I said that, the traditional perspective is that, you fall inside the black hole, and, that actually you feel you don't really experience anything beyond some strange Doppler shifts, but eventually you kind of get, you get sort of pulled to pieces. A modern perspective is that there's a sense in which the quantum effects, even as you go past the event horizon, are quite significant. So, you know, the details of how this happens, it you know, is subtle, and there wouldn't be complete consensus in the literature about, you know, when you feel the quantum effects. But I think the thing that people would agree is that you know, once you've crossed that event horizon, the quantum effects become really important. So again, this is something where it's sort of signaling to us that we need to kind of, you know, we're going to have to go to the forefronts of physics, because we're going to have to combine our understanding of gravity, which is a classical theory. We're going to have to link this with quantum theory, which was the other big kind of paradigm shift of the beginning of the 20th century. So why do we think that we have to understand quantum physics? So in some sense, this goes back 50 years. So Stephen Hawking's most famous discovery is 1974. So reference earlier, he discovered that once you take into account quantum effects, black holes radiate particles. Now, just to pause for a moment, this doesn't contradict the fact that we call them black holes. The rate at which black holes emit particles is really, really slow. So think about having a light bulb where you only emit a photon every 100 years or so. To all extent, it would just look like a, you know, dead. It would be a black, right? And so that's what you should have in mind. So the black hole is absolutely emitting particles, but it's effectively at such a slow rate for these big black holes that it really looks black. But conceptually, it's important that actually these particles can escape. So in 1974, he discovers this. And again, this intuitive picture, which is already shown, is that, you know, you can kind of think about this as being one of these weird things in quantum theory, right? You kind of heuristically interpret it. We know that in quantum theory, things are always popping out of the vacuum. Particles, you know, pop out of the vacuum all the time. But here, if one of them falls into the black hole, the other can escape out to infinity. And as mentioned earlier, the one that goes into the black hole effectively decreases the mass of the black hole. Now, I should say that the picture on the left-hand side is absolutely one of Stephen's pictures. So this is, you know, the information loss paradox. So why is this such a puzzle? So the point is that actually, although the black hole radiates very slowly, if you just wait long enough over the time history of the universe, the black hole will radiate Hawking particles, and it will radiate away just into a bath of heat. So you'll decrease the mass of the black hole, and it will just radiate away into a bath of heat. And that's what you see in the pictures here. So the middle picture, that's your black hole. It's emitting Hawking radiation, so you've got this bath of radiation. Eventually, it's radiated away, and it's radiated in heat. But what he realized almost immediately after sort of formulating Hawking radiation is that this gives a conceptual problem, because if you're radiating away into a bath of heat, how on earth do you know about the history of the black hole? So if you throw away your obsolete computers from 20 years ago into your black hole, and your obsolete computer, again, I really like this picture because it gives you the sense of what information is. You know on your obsolete computer that you've still got information stored there, right? You've got your, whatever it is, your undergraduate thesis or your, you know, whatever it is. So you throw that into there, you throw it into the black hole eventually evaporates. How do we get from that pile of heat what was on the computer that you threw in? So it gives you a real sense. We can never determine the back history of the black hole, how the black hole was formed, how it lived its life, what fell into it. Now, is this just an esoteric problem, or is it something that's to do with quantum mechanics? So I think the single most common question I have is, well, isn't this just a weird thing of quantum mechanics? There's things you can't know in quantum mechanics. And the statement here is actually, no, this is weirder than ordinary quantum mechanics. So absolutely, in quantum mechanics, there are questions we can't answer with certainty. So the poor cat on the right-hand side is Schrödinger's famous cat, where we don't know whether the cat is dead or alive until we make an observation. But built into the laws of quantum physics is determinism, a sense that the physics at one time, the state of the universe at one time, uniquely determines the state of the universe at a later time. And so information loss would go beyond ordinary quantum theory, and it would imply that black holes are not deterministic. Why is that so surprising? Well, actually, the whole formulation of physics assumes this kind of determinism, this sense that the state of the universe at one time uniquely determines physics at a later time. So again, coming back to, why is it the physicists are so interested in it? Again, it's when you've got these big conceptual paradoxes that actually it leads to breakthroughs. So jumping back in time 100 years, when people were thinking about the behavior of atoms in the beginning of the 20th century, and the experiments of Rutherford's and others, demonstrated that there was a cluster of positive charge, and then there were negative charges around it. And people said, well, according to classical physics, surely positive charge and negative charge attracts. Why would the electrons sort of not just fall into the positive charge? And of course, the reason they don't fall in, is something we learn in basic quantum physics. It's because we have quantum theory, we have discrete energy levels, we have in a sense a paradigm shift, which is linked to the sort of quantum uncertainty we've talked about earlier. You can't know the position and the speed of something simultaneously. So that kind of paradox that the fact that we couldn't explain why the negative charge around the nucleus of the atom didn't fall into it led to a paradigm shift. And so people have wondered whether really the question of black holes leads to us to a paradigm shift. So it's back to the drawing board to really question ourselves about what of our assumptions are going wrong. Now, one of these sort of some of these reflections on what was going on in black hole physics led to a very revolutionary idea in physics within the framework of string theory, which is called holography. And so this is something which I think I've worked on for pretty much all of my career. Is really a kind of a paradigm shift. And when it was first presented 30 odd years ago, the reaction was, this is so strange, so crazy, it can't possibly be true. So what is the idea? And it's something that's very hard to get our heads around. The idea of holography is that gravity can be described in terms of something that doesn't have gravity in one less dimension. So the gravity that we feel in this room, we feel like we have 3 spatial dimensions in this room. What it's saying is that if you surrounded this room by a kind of a giant sphere, we could describe what was happening in this room by something happening on that giant sphere in 2 dimensions, but without any gravity description. The picture on the right-hand side is trying to convey that. So again, we've got a picture of the 3-dimensional world. The ring there, for those who are interested in particle physics, the ring there which is shown is the big particle physics collider in CERN. But we've got this 3-dimensional world. We've got kind of gravity in this 3-dimensional world. And then holography says that actually we can describe things in terms of things which are happening on a 2-dimensional shell that lives around that world. Now, if you find that hard to think about because in your everyday experience you experience gravity in 3 dimensions, you're right to find it hard to think about. Just like we find it very hard to think about quantum physics, right? Because it's not our intuitive everyday experience. So this is really a conceptual paradigm shift. So I'm not really going to go through, how they came to this from black holes, although it links to some of the things we've discussed earlier in terms of black holes having entropy that scales with area and so on. But what does it mean? What does it mean for what's going on in black holes? So one of the things is that it suggests that Einstein's picture of the event horizon, this picture that we draw on the right-hand side, isn't really quite correct. It's suggesting that actually as you go into the black hole, there's something which is capturing the quantum physics. So one interpretation, and here I'm getting kind of more heuristic to kind of give you a sense of these ideas. Different sort of detailed descriptions of this do things in slightly different ways. But one interpretation is that as you're going into the center of the space-time, where there is a sort of, the black hole, is that the surface of the black hole and the region behind it is behaving as a giant, kind of computer hard disk. And so actually, as things are stored in that part of the space-time on the surface of this hard disk. But it stores an enormous amount of information. So there's 1 quantum bit of information for every Planckian unit of area. And if you translate that into how much information is being stored in a black hole that has a mass of the sun, it's about 10 to the 50 of these computers. That's the kind of number we're talking about. So that's a huge amount of quantum information, much, much bigger than anything that we're being able to realize with quantum computers in labs. Now, before I go on, so the picture on the right-hand side, drawn for me from one of the artists we work with, that's trying to describe for you, so we're kind of describing sort of the region where the black hole is, the surface of the black hole and the region just underneath it. It's trying to visualize for you that every bit of the space-time, every little bit of the space-time is storing some quantum information. Now, we're used to hard disks in our computers being flat. If you sort of zoomed in on that, it would be sort of flat. But we're saying here it's actually, it's kind of a curved surface. And there's not a sense in which you can kind of really go deeply behind it because everything is very quantum. So another kind of picture to sort of visualize what goes on. So the question of what's happening as you go into the black hole. So we know from, we know that as we go towards the black hole, you're not actually feeling strong forces, but as you cross into the black hole, at some point you're torn up and you're torn into, you're broken up. The idea here is that as you go into the black hole, whether you've crossed into the horizon just behind, actually you're human, you're brave, brave probe, you're brave astronaut that's going into there, you're being torn up into the black hole, and you're actually sort of being imprinted in terms of quantum information. So the visualization you're seeing here is that the black hole is keeping a record of you. As you go in, you're being torn up into quantum kind of information. And the artist's visualization here of sort of the light outside, that's the accretion disk that you've long since passed, right? You've gone deeply into the black hole. Now, there's certainly a lot more to understand. So there's a lot of discussion about the details of how this happens and different sort of mathematical descriptions of it. But I think it's fair to say, I think it's slightly, probably one for the discussion. So if you'd asked people 20 to 30 years ago, 30 years ago in the physics community, will you be able to recover the information of the black hole? There might have been a mixture of opinions. I think the majority has tipped now to the fact that actually information is retained in black holes. It retains the history of what's gone into it, and that will eventually come out in subtle correlations in the radiation. There's a lot to understand about the details, but the whole idea of holography and these ideas linked in string theory suggests that this is, really sort of provoke that this is the case. And to be honest, this is the answer we would expect, because it would be very strange if we had a physical theory which was not deterministic. Okay, so as you go in, eventually we should be able to find out what happened to you, but really not over human lifetime scales, right? We're talking over periods of billions of years the information would come out. So now, what does this have to do with quantum information and quantum computing? So I've given one point already, which is that the amount of quantum information we're storing in black holes is absolutely huge. And in fact, the postulate is that this is the most efficient way that you can store information in nature. You cannot get a quantum computer that's better than a black hole. Okay, so actually, black holes are arenas to think about manipulating very large amounts of quantum computers. The other point is that something which is falling into a black hole is really essentially changing the state of the quantum hard disk. And this gives us a mechanism for thought experiments which effectively involve very large numbers of qubits. Again, I reiterate that the models that we have in the lab have very small numbers of qubits, right? So this gives us a very different way of thinking about things in terms of geometry, which involve very large numbers of qubits. The other kind of intuitive thing is that the shape of the space around the black hole is really important in describing what's going on. And the space around the black hole, you can think of in this picture as behaving somewhat like a neural network. And the layers of this network you can think of as implementing quantum computing operations, including correcting from errors when you make quantum computing. So going into that in detail is not, is beyond the sort of scope of what we're going to do here. But the picture on the right is sort of meant to, again, give you a sort of intuitive sense of this. So this person is looking up. The black dot at the center is meant to be the black hole. And then what we're saying is that actually as things start to fall into the black hole, you can start to think about, the motion of somebody and the interaction between different objects as implementing sort of different types of quantum computing operations. Now, whilst that sounds very abstract, you can actually take those ideas over into just describing quantum computing. You can say, look, we've got the shape of space. What if we put a neural network in that space? How would quantum operations work? And that's definitely something I'm really interested in terms of having more efficient quantum algorithms, quantum computing. So it turns out that actually if you put networks in the kinds of shapes of space that you have around black holes, they're actually much more efficient at processing. Okay, so we've covered quite a lot here. Now, what is the things which are sort of thought experiments, and what are the things that we can do as physical experiments? So many people in these kinds of talks come up to me and say, well, can we go and do this? Can we go and harness a black hole? So Freeman Dyson, the wonderful eccentric physicist, British-American physicist, he came up with an idea for testing for advanced civilizations, which is an advanced civilization would have built a sphere around their sun to harness all of its energy. So the Dyson sphere, as it's called, certainly, the idea of building a Dyson sphere to use a black hole as a quantum computer lies in the realm of science fiction. But after a talk I gave about 10 years ago, somebody actually did go and write science fiction about it, which was quite fun, quite cool. But, so that's not what we expect here. But the kind of thought experiments give new insights into quantum computing. And as I said, the kind of idea that you're thinking about quantum networks in curved backgrounds, which really come from thinking about black holes, that's a very concrete way that we get new insights, and people also think about correcting quantum errors and things like that. So it's a very surprising route from that we've taken from sort of the collapse of stars to physical black holes, right back to rather abstract sort of considerations about what might happen as you fall into a black hole, and linking that to quantum computing. This is exactly why I love the subject. So, black hole hunters, the people who go and make detailed measurements of the black holes, so this is sort of arrays of telescopes, the more detailed measurements we can make, the more we can understand them. So, the gravitational wave experiments, which India is involved with, all these other experiments are wonderful. Right-hand side sort of shows an artist's visualization of what the details of a black hole might look like, the so-called fuzzball sort of suggestion which Nabamita mentioned earlier. So that's really exciting. But actually, we could go all the way from astronomy right back to Earth. So the left-hand side, you're seeing all of these different types of experiments that people use to look at black holes. And on the right-hand side, we're connecting it to what might be the next generation of quantum computers. So there's so much here. There's the understanding the astrophysics, all the things around that. There's understanding the fundamental science of black holes, and there's linking it across to quantum computing. So for those of you who are in the audience who are sort of studying physics or thinking about studying physics, please do come and join us. There is something for everyone here, whether you like taking data, whether you like doing mathematical computations, or whether you're interested in how it links with computer science. It's a really exciting time. So thank you very much.
So, well, thank you to all the speakers for their very inspiring talks. I feel like my brain has been stretched and then spread all over this stage in zeros and ones. And maybe at the end of this evening, I'll have to recollect it and put it back in. So at this point, we always like to have interactions with our audience, and this is the time. And so I'm going to try and see if we can bring some chairs on stage and get all our speakers to come to the stage. And please already just ask questions. Any questions you may have about the talks, keep it specific to black holes and quantum computers, whatever was discussed today, and keep them brief. And if you want one of the speakers specifically to address the question, you can say so, otherwise any of them can. Yes, please, in the yellow shirt, yeah. Yeah, please ask one at a time so that other people get a chance. Then we'll come back to you.
Anyway, so while I was with this talk, I had to think about the Harry Ball theorem that has this, that a sphere can only have one single leg of sphere
Yeah, you really have to keep your question brief. I mean, I was also not able to follow the exact question, but is it about something? Please have a
So,
seat, all of you. It's for you. Please sit.
So let me take
Is it something about? Can you reference what aspect of the talk you're asking about?
I'm asking this question because like because information I was thinking in the angle that information was retrieval as inside Wikipedia to do it, which is traveling in an n-dimensional space and black holes because black holes can be viewed as a singularity. So but in an isometric situation there are no singularities.
Yeah, no, I think this is too long a question. We're not at that level of this talk. So please, can we get back to you later? We'd like to take questions which are brief and pointed about things that have actually been said. So please, yeah, I see a hand there. Yes, yes.
In the first talk, I'm from a mathematics background. I haven't studied physics after that. But you said merging of black holes. So the merging is like if I consider it as like something submanifolds, it's like a connected sum, right? So
no, it's you can take two stars, and then the two stars are orbiting around the common center of mass. They come very close. So it's something similar to that. You think of two black holes which come very close. When they come very close, the horizon actually forms surrounding them, and then the inside becomes that of a black hole.
so the question is something like this possible? So imagine
It's not connected sum. It's not connected.
Okay.
Sum.
So like some strips in between of these black holes like that.
Connected sum is a particular operation that you do with manifolds. Here, in real time, two things are merging.
I think you can think of this as, take two soap bubbles. If two soap bubbles touch, okay, of course they can form a very complicated bubble, or the inside can just go poof and then it's one soap bubble. It's much more like that. Yes, there please.
So I have a question for each one of you. For Suneeta ma'am, can black holes eventually disappear completely or they leave behind remnant?
So there are theories that they leave behind a remnant, but the consensus, so black holes can also completely disappear if you believe the Hawking radiation picture, and then they leave behind radiation which may or may not have information about what formed the black hole. So that's still an object of active research.
Please pass the mic. Whoever has the mic, please pass it back. Who has the mic? Somebody has to have the mic. Yeah, okay. Yeah.
For Nabamita ma'am, could black holes be fundamentally different objects than predicted by general relativity, such as fuzzballs or graveyard stars?
Fuzzballs, I would say that okay, that's also a proposal, but believing on that, then fuzzballs are what will give us finally the effective description as black hole horizons. So it is the same thing. Okay. And what was the other thing that you said?
Graveyard stars.
Yeah, okay, so, yeah.
And for Marika ma'am, can quantum computers will be helping realistically the black hole evaporation to stimulate the black hole evaporation in the near future, and which benefited so far quantum computing from black hole physics or black hole physics from quantum computing physics?
Okay, so to take these things, there are some discussions about doing quantum simulations to help understand black hole physics. I personally think they won't give very much new insights into black holes, because ultimately the systems that we're simulating, we understand the physics very, very well. And so to connect it with black holes, we have to make kind of assumptions, and we'd actually like to test those assumptions, right? So whilst I think it's very interesting, some of the simulations they're doing, it's probably not going to give fundamental new insights into black holes. Black holes versus quantum computing, which has given them more insights, I think we're in very early days of these things, right? So at this stage, I think it would be too preliminary to sort of answer. I think my observation would simply be that 20, 30 years ago, we wouldn't have expected these fields to connect at all, right? We saw them as very much disjoint things. And the fact that these fields are interfacing, and that we're actually able to think about things like correcting errors in quantum computers using black hole ideas is itself sort of remarkable.
Okay, thank you to all the professors.
Yeah, please. Do we have only one mic circulating? Do we have another one somewhere? Oh, this is the other one.
So the thing is, the fact that nothing can escape. Yeah, so I think he's asking whether a particle falling in and another one going out, isn't it opposite to saying that nothing can come out of the black hole? That's your question, right? Yeah, so the thing is, that's only true classically, that nothing can come out of the black hole. Now we have a scenario where we have quantum matter outside the black hole. And although Hawking's calculation was classical black hole and quantum matter, the moment you have quantum matter, quantum matter can create this particle pairs, okay, of which one has negative energy and the other has positive energy. There is a chance for the negative energy particle to go inside the black hole, not a chance for the positive energy particle to fall in, because then the negative energy particle would exist outside, which it cannot. So these particles pairs are formed only for a very short time. But in that time, if the negative energy particle goes in, then it decreases the mass of the black hole and something comes out. So that's a phenomenon which you see when you have quantum matter outside. Earlier, everything was done with classical matter.
It's
because
a
it has negative energy.
Negative energy particle.
So it has negative energy from the perspective of the outside.
Let me say that Hawking issued a lot of warnings when he gave this analogy, and actually Hawking's paper is not based on this analogy. Hawking's actual paper does
calculation.
he does a hard calculation of how the quantum vacuum behaves near a black hole. Black hole distorts everything, so it also distorts what is the meaning of empty space, and it distorts it into a space which is actually at a temperature with radiation flowing out. This is a hard calculation, and he gave this model, and you're right, it's full of weird things that we are supposed to believe.
It's very influential.
It is influential. It's influential. People use it for intuition, but you shouldn't believe it only because of the model. It's really the calculation. Someday maybe you'll read the original paper, and then you'll see that it's a different.
In fact, you can do that semi-classical computation and can exactly get Bekenstein-Hawking entropy. So it's like that.
Please. Where's the mic, please? Who has the mic?
Can I ask a question?
Hello.
Can I ask a question?
I had a question regarding the Hawking radiation explanation about the entangled particles. If the emitted particle, the positive energy one which goes outside, is observed, as the particle is entangled, would the entanglement change any properties about the black hole?
That's that's a subject of active research, right? Is there an entanglement between what went in and what went out? And that has something to do with whether information comes out in the black hole radiation or not. It's still a subject.
It's actually a very interesting question. I think in the last 10 years, research has focused a lot on that exact question.
Yeah, so Einstein had said that the signal between a electron and a positron travels faster than light. So will that be able to escape a black hole, and does it have anything to do between the negative and positive charges of the matter and antimatter in Hawking radiation?
So I think we're discussing amongst ourselves, but the answer is that really nothing does travel faster than the speed of light, right? So you can't propagate signals faster than the speed of light. There isn't a way around that.
So in fact, Einstein never said that between an electron and positron, the signal travels faster than light. I don't think he actually said that, but if he said that, I think it was wrong. So it's not a contradiction.
like an elementary. How similar is that to an elementary particle? And that's definitely something that people think about. So very big black holes, macroscopic black holes, there's a sense that we're still defining them by the gravity, the fact that, you know, they're curving space around them. You have very small black holes, primordial early universe black holes. They are probably best thought of as much more similar to particles of what you described.
And actually, I think the idea originated in a paper of Hawking. At least that's where I first saw it. Sorry, there was someone there, but you wait, I think. Can someone get the mic over there? You can just pass it to Suneeta.
Good evening, and my question is regarding one thing that Nabamita ma'am mentioned in her talk. So you said you were talking about black holes with multiple event horizons. Yes. So I understand the first one.
Multiple horizon. One of them is event horizon, and then you can have other horizons.
Okay, so could you explain what the other horizons stand for? What is their function? Because the event horizon practically is the limit inside which light cannot escape. So what does the second or the third horizons do?
Okay, yeah. So if you remember the picture that I was showing, so there was this event horizon. Then I just tried to keep it black. Then I had another horizon, and then I made it like blue. So I didn't really explain it to you. So what you can, so if you just look at the metric and then try to understand what is happening to it, how the signature of the space and time is changing, you will see that when you cross the first one, you can kind of think of like space and time being changed, and then again you can cross the second one, it will again differ. It will again be different. So it's like there are multiple points where you will see curvature singularities coming. Those are not space-time singularities, but that's happening in 2 points. So that's what these things are doing. And of course, they have more physical effects on the system. But yeah, these are like...
Maybe one way to say it is that, you know, a black hole horizon is a place where space and time gets warped very badly at a definite point, at a definite distance. And in double horizons, the space again gets warped very badly at the second one. But it's the outermost one which tells us that where the signal is trapped. If it crosses into the outermost one, then it's gone inside.
So that's what we will call always the event horizon.
That's the event horizon. But the others also, each one of them, there's a twist in space and time. Yeah, yes.
Computation doubles every year. That is what AMD and Intel are doing. But we are now hitting the Moore's law. But in the quantum computing case, the amount of qubits are increasing day by day. I think 1000 is what we have reached by now. Will there be a Moore's law on qubits?
Yeah, so I mean that there will definitely be limits on what we can do with quantum computing, but I think we're far off what we can actually realize. I think the real question is that you sort of said is actually getting beyond the current sort of 1,000 to 10,000 to 100,000. And by the way, something I didn't say in the talk is as soon as you get to a 10,000 or 100,000, you start being able to do quite interesting things. So that's the kind of threshold you need to break, for example, standard encryption, which is used in all our financial transactions. So companies such as Google are announcing recently that, you know, as soon as 2030, we may really have problems about quantum computers being sort of able to actually sort of harness and break encryption. But that will be still a long way from the sort of analogs of limitations of quantum. You know, the limitations are really sort of this scaling up and actually getting larger numbers of qubits and getting them to operate well.
Will there be instability, or will there be architectural limits on how many qubits you can fit within a space? Because in current physical traditional computing, we are going 3D and 4D.
Yeah, I mean, so you're sort of touching on the fact that, you know, people frame the challenges in different ways, right? And sort of, you know, there are different kinds of challenges in terms of sort of stability and in terms of sort of environmental contamination, in terms of actually being able to really control this from a lab perspective if you're using complex things like cold atoms or so on. And then there are sort of different sort of, you know, more sort of fundamental limits on what you could actually do. I guess if we really got into sort of far fiction in the far future, you know, those of us, you know, so quantum computers are harnessing essentially electrons and photons, right? You know, in the far, far future, you would say, well, actually, are electrons really fundamental particles, or are they made up of sort of constituents? And could you actually, you know, kind of go further with that? But now we're jumping way into sort of science fiction in the far future.
Thank you.
Yeah, just 1 minute. So we have a question here, and so while the mic travels here, if the volunteer is available, there he is. Okay, but before you ask the question, let me just say we had a question from the YouTube live feed. First of all, we had many complaints that the live feed was lagging in the first half, and I heard from our people that we were facing some trouble. So those who are listening now on the live feed, we apologize. I believe it came back in the second session. The question, there's a nice question. It says, why do we believe that the massive object at the center of each galaxy is a black hole? Why couldn't it just be a star?
So I think that whatever we know about the black hole at the center of the galaxy is from the stars surrounding it, and we have the Event Horizon Telescope image. But I think the strongest evidence for black holes comes from the LIGO signal.
Yeah, but that doesn't apply to it's not the supermassive black holes that purge. So
not.
I guess go ahead.
So I think that the picture I showed about, you know, things which are orbiting, say, Sagittarius, actually the fact that this has the characteristics of a black hole from Einstein's theory, sort of, you know, that it's following the orbits, that's something which is a kind of you know, consistency. In terms of being a star, well, our usual picture of star would be something which is much smaller, which is building plasma. We're talking about something here which is million times heavier. So it's already very different from kind of stars. So that's a distinction. In terms of people's ideas about how galaxies are formed, you know, they have ideas about how these things would have formed. You know, they call them active galactic nuclei in terms of sort of accretion and so on. But, you know, still the question is very well founded, because the images, you know, from the Event Horizon Telescope are very beautiful, but they still sort of struggle to pin down more than how heavy it is and perhaps how it's spinning, you know, and so actually really getting more handle on it to sort of test, is that an object like the object in Einstein's theory, or are there ways it would distinguish? We would absolutely be waiting for things like the gravitational wave detectors in space, which will actually be seeing gravitational waves which are associated with those, and would be much more sensitive to the details of the geometry around it.
Thank you. So there's a question there, yes.
Hi. So I have very small two questions. One is about this particle-antiparticle, again the pair production. Suppose I take a fuzzball picture, and now how does this particle-antiparticle pair work? Because now it can smoothly interact with the fuzzball. There is nothing strangely happen. And okay, can I ask the second question, or?
Should we take the first question first? So I think, you know, the idea in a sort of fuzzball type picture is that really the space-time description around the black hole is very, very similar to what happens in a black hole. So there's still a sense of, if something goes in, it's trapped for a very, very long time. The point is that the fuzzball is, you know, resolving the space-time within the black hole in a quantum way. So it's still mirroring all those properties that you expect of the black hole, but the subtle difference is that when the Hawking radiation comes out, it will not be exactly thermal. It will capture the history of the thing that's gone in. But the picture I showed that came from the New Scientist magazine, the fact that that looks very much like a black hole, that's the reality, right? Because, you know, to a very high approximation, this fuzzball is really capturing the same physics as the black hole.
Yeah, my second question is also small. So, like, ma'am, you shows that singularity will be the 1 point, but suppose I took the non-commutative space, like xy coordinate are non-commutative, then will the structure of singularity will change, how does the general relativity goes in that picture, and will I get something new interesting physics when my underlying space is non-commutative, like xy bracket is non-zero?
So I think my take on that would be that, you know, people of course have some ideas about, you know, playing with non-commutative geometry and so on, and they've done this particularly in the context of particle physics. So I'm thinking of Alan Kohn and others. But actually, the reconciliation of that with general relativity, that's not something we understand well, right? So you would be modifying general relativity, and that's not something we get. I don't know whether anyone wants.
So also, it's not always a point singularity. So rotating black holes have a ring-like singularity.
Good evening, ma'am. I have two questions. One is like, suppose somehow I survive the tidal forces and I enter the event horizon, and now I am falling towards the center of the black hole. My back is towards the center of the black hole and I am facing the event horizon. How will the external world appear to me? Like, will I even able to see it? And if yes, then how will that external world appear to me is the first question. And the second question is that while falling, suppose I shine a light, a torch or a laser towards the event horizon, like opposite, away from the center of the black hole. So will I see the light behave exactly the same, the way I see it here?
Yeah, so anything, you're at some point in the interior of the black hole and you shine light, it will always go back to the singularity.
So like I will see the light moving backwards rather than moving forwards, that way?
You'll see it going forwards.
All the light rays going towards the singularity.
You'll see it going forwards and sort of curving. I mean, what you see, I don't know, but it will.
Like I am falling towards the singularity.
Yeah, you are falling.
And I am shining the light simultaneously. Yes. So how will I see
Every
the
light ray will go out to the singularity.
See, it's because space and time are distorted. So the light ray may exit from you pointing towards the outside, but as it travels along the line of least distance, it will actually come round and reach the singularity anyway.
So I will
not
see
from
it
the
like
same route. And this is often said in the following words: the ingoing direction is ingoing and the outgoing direction is also ingoing. This is the beauty of space-time being warped. That both, you have asked a very good question, because outgoing direction should be outgoing, right? Not inside a black hole.
And my first question, like how will the external world appear to me if I am falling inside
Every trajectory of everything that you see around you will be going towards the singularity.
So I will like see the center of the black hole only, even if my back, I am turning my back towards it. Okay, thank you.
Hello, excuse me. Here. Good evening to all. Thanks for the informative lecture. I'm not a physicist. I have a generic question, a thought question, and to the panel. This is what I got from the discussion. Are we itself, because the universe that we live in is expanding, at the point of Big Bang, did we enter a black hole and we are expanding it, and the entire universe is kind of a laid out qubit structure where the information is getting built up gradually, which as an earthling we are not able to decipher, and probably that might be the reason that we are not able to connect with some intelligent life form? This is a very thought question, nothing with respect to this. I would like to know what panel thinks about it.
I don't think we are inside a black hole.
Why not? I think
we could be. We could. I can send off light rays in all directions. Right?
Everybody's inside the black hole.
No, I can send off light rays in all directions. Okay, everybody could be inside. No, but
I
then
mean,
I
at
would
least
have
my view would be that we could all be inside a black hole, but all the whole universe, all the other planets, stars, galaxies are all inside the same black hole.
That's
that
what
we
my-
can't, I think, rule out, can we?
So I think I would disagree with that in the sense that, so I mean, the question came earlier about inner horizons, and you sort of talked about what they would be, but actually the analysis of this suggests that they become singular, right? So any kind of inner horizon becomes singular. So whatever kind of black hole you have, that there's always a singularity. And in that sense, the fact that, we would know if we were in causal contact with a singularity, sorry, a technical phrase there. So I don't think we can be inside a black hole. So we would see more distortions, right? So that
question.
Possibly because the Earth is, the universe is too big to, the black hole is too big to check that in a human lifetime or in the time span of the entire universe. I don't know. Let me just say that this is what you raised is a speculation people have brought up. Please, Costas.
But if it's sufficiently unobservable, then I think we get philosophical.
Okay. Anyway, let's agree that it's a very speculative idea and that one would need a calculation to pin down whether it's even possible. I think we also haven't really done it, but it seems very unlikely. Thank you.
My question was that you said that the radiation will evolve from a pure state to a mixed state. But for such a thing to exist, the time symmetry should be broken, which is violating some postulates of quantum mechanics, like because a pure state can't be, you can't apply an evolution operator and then make it into a mixed state. Like, why is that? How it works?
That's the point, right? Quantum evolution cannot take you from a pure state to a mixed state. But what you find when the black hole is completely radiated away is you end up with a mixed state. That's the contradiction. That is the information loss pattern.
Why is it called the information loss? Because
You lost all information about the state with which you began.
And how do we know that whatever the way in which the black holes are formed, they will always end up in the same state? Like, I think that's what I understand.
That's what you're seeing, right? See, suppose you do the calculation. Tells you that whatever the black hole was formed from, whatever went inside it, eventually you end up with thermal radiation, which is only characteristic of a certain temperature.
We are only able to measure only this radiation.
Yes, the calculation predicts that everything will evaporate away. It will take a long time to evaporate, but it will evaporate away and give you thermal radiation.
Please tell us your name and
मेरा नाम है अबीर खान.
I think we should give him this here.
हाँ, हम हमेशा ब्लैक होल को फोटो में एक साइड से ही देखते हुए आए, तो प्लैनेट के तरह उसे चारों तरफ से देख सकते हैं.
Nice question. So, Marika, he says, we always see a black hole from one side, but like a planet, can we try to see it from all four sides?
तो बहुत सारे ब्लैक होल्स हैं जो गोल हैं, ठीक है? तो आप किसी भी तरह जगह से आप देखेंगे वही वैसे ही लगेगा, अंदर से काला लगेगा.
Hello ma'am, my question is specific to Marika ma'am. When we are comparing black holes with respect to quantum computer, there is a line in your presentation. There is a 1 qubit of information for every Planck's unit of area. If I imagine a qubit as a plot sphere with a state vector and it's in a superposition, how these analogies are comparing? Like, I don't understand.
Okay, so I think it's where, in a sense, the heuristics and the pictures break down to some extent, because, and it also comes to Sunil's answer earlier about, we can't really give you intuition about sort of particles where we're actually describing things in terms of quite complicated mathematics. we have a picture of, so the usual quantum bits we're thinking about, we think about them in terms of, say, electrons. It's a good analogy, right? An electron or a photon. But actually, the degrees of freedom within, quantum degrees of freedom underlying gravity, they're at much, much smaller scales, right? So in each sort of unit of area, which is equivalent to the size of an electron, you would have many, many degrees of freedom. And so we're saying if you broke that up into sort of little tiny things, to some extent you can think of associated with it, every little block of space-time, sort of a degree of freedom, which is a quantum degree of freedom. Where the analogy breaks down is that we can't really treat them as individual different things. We have to treat them very much as sort of collective things, right? And so the mathematics that describes it is a bit more complicated than the mathematics that we describe to, just individual sort of quantum bits. But the basic answer here is that for every block of space-time, you can break it down into, tiny, tiny bits of that block. Each of those sort of tiny bits actually has a quantum degree of information associated with it.
Okay, and one more.
Sorry, I think we are really out of time. Sorry. Okay. So actually, I'm really sorry. I mean, but your brother has asked a question already. I think we have to stop. As Nabamita said in her talk, the geodesic sometimes terminates in finite time, and then it's the end. And our geodesic has just reached the end. Marika has to take a car to Mumbai and get a flight back home tomorrow. So I want to close by thanking all of you for coming, and I feel, and all of us here feel very proud that you took your time to spend several hours with us and listen to our stories about black holes. I hope you'll read more on the subject, and I also want to tell you that we are hoping to have one more event like this, more on the observational side perhaps, maybe in September or October. So please stay tuned for that. Thank you all for coming. And please give a big hand to the speakers.